Okay, in this video, I hope I can get it into one that's only 15 minutes long max. I'm going to show you how to do a Fourier series on a different interval. Instead of just negative pi to pi, we're going to go negative L to L, L for being length. But before we do that, you should have done this problem right here, done this Fourier series right here, and gotten all this right here. So you should have had negative 2 over pi n times this thing. And I wanted you to write out the first handful of terms here. So hopefully you're good with that. And now we're going to go down to here. You also should have done this one. And you should have gotten this thing right here. Pi over 2 plus all this stuff. So what I want you to see is something that's kind of magical with these. If you look at this thing, you can see what I've written. I wrote integrate. Why did I write that? Well, what is this height right here? It's negative 1. And what's this height right here? It's positive 1. We spend all this time doing Fourier series, but we can also do things to them. We can do calculus to them, which is kind of wild. So if you look down here, I already wrote this. Here in this like upside down absolute value function, here the slope is 1, and then the slope is negative 1. So what I want you to see is that I can take the derivative of this thing. If I take the derivative of this thing, it would be 1 and negative 1. What I want you to recognize is that if you take the derivative of this line right here, and you could work out how to take the derivative of this line, there would just be a little bit of chain on this cosine. The n would come out front, cancel with those. These would still be here. The cosine would change to a sine, and we would have a negative out front because the derivative of a cosine is a negative sign. Notice, if I do that, we should get almost what we have up here. All of those cosines go to sines, all the n's cancel out, all of the I want you to take note yourself. The only thing that's a little bit different is that this one is negative 1 and 1, and this one is 1 and negative 1. So if I were to apply a negative to all of these, it would match the derivative of this thing right here. You can imagine I can also do the opposite. So that gives us a new way to calculate Fourier series. Say I wanted to calculate the Fourier series for something like this or for something like the absolute value graph. Well, I know you guys are like actually really good at integration by parts, but and you could do this one, but if I integrate this one right here, I get the negative version of this one, and that just becomes another connection to all these Fourier series. All right, so hopefully you're good with that, and hopefully you had a little practice doing some Fourier. We're good to go. We're good to bounce into the next thing. So let's go down. All right. So far, every Fourier calculation that we've done has had an interval that's gone from negative pi to pi. So you may be like, but things aren't always from negative pi to pi in our real life. Well, we can fix that problem. We can go from negative L to L. And then we can do other things too to make it so that it's not just centered over the origin. But for the purpose of this course, we're only going to go as far as negative L to L. Let me zoom out. I'm just going to try to keep this easy, to be honest. So for Fourier series from negative pi to pi, we do 1 over pi, integral from negative pi to pi of f of t times cosine of nt dt. Well, if we want to switch the pi's to l's, you know, it should make a lot of sense that, all right, anywhere we got a pi, we're going to just replace that with an L. So this should make sense, this should make sense, and this should make sense. Where does this come from? Notice if L was pi, I would get a pi here and a pi here. They would cancel and would give me cosine of nt. So this formula fits what we already know for intervals from negative pi to pi. And you know what? It works for any interval that would go negative L to L. Here I go through like a process of explaining where it comes from, but to be honest, I'm not really worried about it at all. We're just going to roll with anytime we have a interval from negative L to L, then this becomes the innards of the cosine or of the sine that we're integrating. Everything else is exactly the same as what we're used to. And really, this is just matching the period. I'll say it as quick and as succinctly as I can. The period of a regular sine graph is 2 pi. The period of this graph right here is going to be exactly 2 times L. So what we do is we match the period of the biggest one to the period of and that would be with n equals 1. So at that n equals 1, I want the period to be the period that spans the entire length of the interval that we're working with. It's this. Let's roll with it. So I'm going to walk through an example here of a Fourier series that goes from -1 to 1. So this works out kind of nicely, to be honest. And we're going to do f of t equals t squared. So this thing actually has a period of 2. You can see it would look like this. We go up, down from that 1 to 0, 1 to 0, 1 to 0 repeatedly. L in this case is 1 because I'm going from -1 to 1. See if you can go ahead and set up that interval or that integral. And we'll walk through it. Oh, what trick can we take? This is a what function? Ah, you're right. It's even. So I can ignore all of the odd components, which if I can do the alphabetical thing in my head, all the bn's are 0. Is that right? I think I got it right. Okay, so yeah, bn's are 0. I didn't look down. I thought it through, I swear. All right, so an is equal to 1 over L, negative L to L, f of t, blah, 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 blah. So when I take L equal to 1 and I do my even tricks, I'm going to go 2. Well, here, so in blue is what it would be. It would be 1 over 1 would be out front. Integral -1 to 1 of t squared cosine of pi n t dt. But then I'm going to say, nah, I ain't doing that. I'm going to change it so that I can do my even tricks because I'd rather evaluate integrals at this 0. So you can see here, pretty standard. We do our integration by parts down to 0. I integrate on this side. This might be the messiest part of these when we have these other intervals is like dealing with the chain rule mess out here, right? Instead of a 1 over n like I would have gotten before, I get a 1 over pi n. You just have to be really careful, and you can notate it however you want. I use some parentheses. For this one, for example, you could have written pi squared n squared. So we do our integration by parts. I do my multiplication. We get this thing, boom, 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 boom. You should be able to work through all these. It's really familiar. This 2 comes down, evaluated from t equals 0 to t equals 1. So let's do the t equals 0. I'll walk through these. You should know that all of the signs, because look, I do sine of pi n t. When I plug in t equals 1, I get sine of pi, which is 0. When I plug in t equals 0, I get sine of 0, which is also 0. So this is 0, and that one is 0 at both of these. That's what I mean when I say 0 for both, right? And then I just got to look at this one. So this one right here is going to give me what we're kind of used to getting, that cosine of pi n. That cosine of pi n times this thing right here, evaluated at t equals 1, which gives me a 2 over pi n squared, which matches this. My 2 comes down. And then, look, this is where the even-odd tricks are convenient. Plug t equals 0 in to this one. Well, that will make this 0, which makes the whole thing 0, which gives me this nice, easy thing for my, ANs. So I can simplify that by moving the 2 in and then writing this as -1 to the n. So that's my an. And then my a naught is 2 integral 0 to 1 of t squared. Remember, I just take the cosine of nt. You could work it out. Works the exact same way. That, when I plug in n equals 0, becomes 1. So just do integral from 0 to 1 of t squared. Doubled. Use a even odd trick there. You could also, if you didn't remember to do the 2, you could go -1. Either way, you should get 2/3, and that's my a naught. And then, remember, we got to do a naught divided by 2, 1/3, plus here is my 4 over pi. That's here. Sigma n equals 1 to infinity. And then I wrote the -1 to the n over n squared here, times cosine of pi n t. This thing right here, I didn't have it up earlier. The innards here is going to be the same as the innards as what you had whenever you did your AN or your BN calculations. This is going to show up on our, if we plug in a Desmos or whatever we're doing with this thing. So I get 4/3, and then if you look here, I wrote out a handful of these things, and you could graph this on Desmos, and maybe I will. I'll hit pause. So here we go. We get y equals 1/3, blah, 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 all the things that we had over there in our handwriting stuff, whatever you want to call it, that I worked out. Here's a equals, oops, I can't go backwards to a equals 0. A equals 1 gives me that cosine curve, and then watch what happens. I get this nice little, whoop, whoop, check out that parabola that repeats for forever from -1 to 1. How cool is that? All right, now it's your turn to do some. So I will see you soon. Bye.